Yes, guys. So we are continuing with question number 13. In this 13th question, what we have done, the given question is prove that Pn is equal to root pi gamma n divided by twice a power twice n minus 1. This is 2n minus 1 gamma n plus r. Now from first equation, first question, we have this gamma n plus 1 into 2 raised power n, this one. From question number 1, this solution I am finding out. From question number 1, we have 2 raised power n gamma n plus r equal to 1 into 3 into 5 up to twice n minus 1 into the root pi. Okay. This we have taken from the question number 1. Now what we have to do here, let me write this first twice n minus 1 and under pi in the end and 5, 3, 1 in the end. Okay, that will be the equation. Now in the right hand side we have to multiply by in the numerator and denominator of this. Let me write in the denominator of this, or dividing this equation by the right hand side by twice n minus 2. Here twice n minus 1, twice n minus 2, twice n minus 3, twice n minus 4. Even here odd numbers are there. This is odd number 1, 3, 5. Even numbers are not there in the numerator. We have to multiply the numerator of this equation, right hand side, by twice n minus 2, twice n minus 4, 4 and 2 in the end. Okay, in the numerator means in this equation, and in the denominator also. What do we get in the right hand side? So multiplying this equation by this one on its right hand side. Okay, in numerator and denominator of its right hand side, or in its right hand side, in its RHS. Only in right hand side we have multiplied in the numerator and dividing by the same value. What is this? Twice n, we have multiplied in the numerator by twice n minus 2, or twice n minus 2, twice n minus 4, means by even numbers, 4 and 2 in the numerator. And in the denominator also, the same value we have to divide also twice n, twice n minus 2, twice n minus 2, twice n minus 4, twice n minus 4. Even next number, twice n minus 5, and then twice n minus 6, etc. And 4 and 2, 4 and 2. In the numerator, what do we get here? We get in the numerator this twice n factorial, because twice n minus 1, twice n minus 2, twice n minus up to 1. This value will be factorial twice n. So I can write it as 2n factorial in the numerator. Into under root pi is what we get. Into under root pi. Okay. From first question, this first equation, question number 1, I mean, we have this twice n to the power n. This already we have proved in the first question. And under root gamma n plus half equal to 1 into 3 into 5, twice n minus 1 equal to pi. All numbers are there. Now in this case we have multiplied numerator and denominator. In this equation we have multiplied by twice n minus 2, twice n minus 4, 4 and 2. In the same way we have divided by the same numbers, twice n minus 2, twice n minus 2, twice n minus 4, twice n minus 4. Even numbers we have taken in the denominator. In the numerator, which was in the odd numbers, we have multiplied to the even numbers also. We have obtained this twice n factorial in the numerator under root pi and divided by, let me take 2 common here. It will be twice raised power n common, 2 into 2 into 2 into 2 into up to this 2 n times. So this twice n to half of this number means n times. N times 2 will be multiplied. And then we are left with first is n into n minus 2 into n minus 2, n minus 3, and so on up to 2n to 1. So this is factorial n. Now we can write it as factorial twice n under root pi, and then divided by, this is 2 raised power n into factorial n. Try to understand, this is n into n minus 2 up to 1, this is factorial n. So from this equation we have obtained this is twice raised power n gamma n plus half. Okay, this we are carrying on the left hand side. Cross multiplication of this and this will give us, let me write in the numerator here, in this. If we write here, what is the value of that? Okay, so that value we obtained here is after cross multiplication that factorial n is factorial n in the numerator divided by twice n factorial in the denominator. We have this is equal to, what do we get here? Now this is underneath pi only. Okay, so underneath pi in the numerator we have root pi divided by this twice n, twice 2 over n, 2 over n will be 2 over twice n, equal n plus n. And this is our same power added up. This factorial n we have taken to the numerator. So here this gamma n plus half from left hand side will come in the denominator. So this factorial n upon factorial twice n will come here, and this underroot pi in the numerator is left divided by these two numbers, twice raised to 2 over n and gamma n plus half. We have taken in the denominator. So this is underroot pi upon 2 over twice n. Why? Because 2 over n and 2 over n. This is 2 over twice n equals 2 over n plus n twice n. This is, let me take the equation number. First here, let me take the second equation now. Okay, now what we will do, left hand side, now we have what? Bn, beta nn. For the value of beta nn, now let me find out that. This value, okay, if beta nn also we calculate factorial n upon factorial twice n, we will find out, we will equal these two values in terms of bnn. Then bnn value will be calculated. Then we will prove that bnn is equal to this. The left hand side is bnn also. Beta nn is equal to, we know that this is nothing but gamma n divided by gamma n plus n. This is the formula. Beta n is equal to gamma n into gamma n divided by gamma. Sorry, this is n plus n. Gamma n plus n. This is the formula. Since beta n is equal to gamma n divided by gamma n plus n. This value we have obtained. Okay. From this equation, beta mn is equal to gamma n. So here it is nn, not mn. So in place of n, we have substituted only n. N. This is the value. Okay, now let me solve it further. So what do we get here? We write it here. This, for one gamma n, let me change it. This is gamma n is factorial n minus, or let me multiply this by n. If I multiply this by n, or let me multiply this by twice n. Okay. If I multiply this by twice n, we get 2 into n into gamma n divided by gamma twice n. But this 2n, or let me multiply this by n only, this is gamma twice n. If I multiply this by twice n in the denominator also, so what is this? This is twice n, gamma twice n, this is twice n plus 1, gamma twice n plus 1. But we have not put for each of the okay. Now we have to find out factorial n. If I, this n gamma n is factorial n. In the numerator we get, let me write it here. Okay, so this is, okay, 2 into, this is factorial n. Okay, now this is twice n into this twice n. This gamma n is factorial twice n minus. This is, when multiplied by twice n, this will give us factorial twice n. This is factorial twice n. This is factorial n because n gamma n is factorial n. Why? Because gamma n is factorial n minus 2 into n. This will give us factorial n. Let me write this n gamma n equal to factorial n. Why? Because n into this is factorial n minus 1. One lesser than this. So n into factorial n minus 1 is factorial n. This is going to be factorial. This value will give us factorial n. Now this twice n into gamma twice n goes to factorial twice n. In the denominator into gamma n, this gamma n is added as it is divided by. In the denominator we have factorial twice n. This value. Why? But this is factorial twice n minus 1. When we multiply with twice n factorial twice n minus 1, that is factorial twice n. So what we obtain here is beta n value of beta n with this value. Since this is equal to this. Now here, what do we get? This factorial n upon factorial twice n. Factorial twice n is equal to this value. This implies that factorial n upon factorial twice n. That we write here is the twice n factor is equal to these two values. For this value twice n to gamma n will come in the limit of this equal to beta is n divided by 2 into gamma n. So twice into gamma n. The factorial n upon factorial twice n is left over. We have taken this twice into gamma n, we have taken to the denominator of this value beta n upon twice into gamma n. This value we have obtained. Okay, so this value is the third equation that we write here. Now if we compare the third equation and second equation, this is factorial n upon factorial twice n. This value we can write here factorial like this. So the same value factorial n upon factorial twice n, this value from second and third we obtain this value equal to this. Right hand side must also be equal. From second and third, let me solve it here. From second and third, left hand sides are equal. Left hand sides are equal. So right hand side will also be. Right hand sides will also be equal. Will also be equal. This implies that this value equal to this beta n, or we can write beta n upon 2 into gamma n is equal to this value under root pi divided by 2 raised to 4 twice n into gamma n plus half. Okay, this we have obtained from third and second equation. So what did we get? Vn is equal to therefore this we have to take these two, this side. This 2 will come here, but when 2 will come here and we take the denominator, this power will be 1 minus. This is under root pi. Okay, under root pi into gamma n divided by 2 raised to twice n minus 1. So this 2 will come in the denominator if then its power will be negative minus 1. This twice n minus 1 into gamma n plus half. So beta n equal to under root pi gamma n. We can write some negative power. So under root pi gamma n upon 2 raised to 4 twice n gamma n plus half. This is the depth of beta and gamma functions, which are known as first and second equilibrium, Euler's integral or integrals, or Eulerian integrals. So Eulerian integrals or Euler's integrals, we have beta and gamma functions. This is the application of that. Those two functions, those two equations or integrals in the same. So Euler's integrals, those two important Euler's integrals are known as beta and gamma functions, which we have already defined that what are Euler's equations. So Euler's equations, beta and gamma function. First Euler's equation is known as beta function. The second Euler's function or equation is known as gamma function. All those functions we have already defined, and now gamma function, the relationship between beta and gamma function that we have already defined. Here we can say that gamma n, the second Eulerian function, is defined as gamma n equal to 0 to infinity v raised power minus x raised power n minus 1 into dx. This is Eulerian's second function or second equation. Euler's second equation or second integral in this. This will be second integral. This is second integral. Gamma function. Beta function, this is going to be equal to beta mn given by 0 to 1 x raised power n minus 1 into 1 minus x whole power n minus 1 dx. This we have already defined. Beta function, gamma function, gamma n is defined like this. This is known as second Euler's integral. This is first Euler's integral. This already I have defined. This application. These questions are application, further application. This is further discussion on beta and gamma function. This is that question number 13 is complete. Now let me take 14 question. What is question number 14 say? Let me check it. Now question number 14. Let me discuss about it. Question number 14 will show that beta mn, let me write it first. Beta mn is equal to beta, okay, what is beta m plus 1 and n, beta m plus n plus beta n plus 1 or 1 plus n. Yeah, 1 plus n. So beta n plus 1 and beta n plus 1. This is we have to define. We have to show that beta mn is equal to these two, sum of these two beta functions. So this we have to prove here. Now let me take right hand side here. So right hand side looks out to be larger one. So this is true for being, let's say, solution here. Right hand side. I'm taking the right hand side. Right hand side is beta n plus 1 n plus beta n 1 plus n or n plus 1. No problem. Now, what is the definition of beta n in terms of gamma function? Let me define that. Beta n is n plus 1 into gamma n divided by gamma n plus 1 plus n. This in terms of gamma function. The relationship between beta and gamma function is defined like this. Or we know that written like this. Since beta n is equal to gamma n divided by gamma n plus n. This we know. Okay, so because of that, this we have defined like this. Beta n is gamma n plus 1, gamma n divided by sum of these two, gamma under gamma, sum of these two, n plus 1 plus 1. Okay. And plus sign. Similarly, the second one plus, let me write the second part also. Second can be expressed in the same way. Gamma n plus 1 or 1 plus n, no problem. In the denominator we have n plus 1. The same in the denominator. We can take LCM here, or first let me define this n plus 1. This is what we may say. This is gamma n n plus 1 is n gamma n. This is nothing but n gamma n as it is. N plus 1 is gamma, meaning that gamma n plus 1 equals n gamma n. Since this we know, because of that n plus 1 gamma n plus 1 is n gamma n as it is, divided by this letter. This is n plus 1. You can write it as n plus n gamma n plus n. No problem. Region is like this, n plus 1. Whatever in place of n, we subtract 1 and write n gamma n. So Similarly, we have subtracted 1 here. It will be n plus n, it will be n plus n, gamma n plus n. Okay, similarly here, this sign gamma n as it is n gamma n, it will be n gamma n into divided by, similarly here, n plus n gamma n plus n. Now if I take gamma n common, or gamma, okay, this gamma n common, this is gamma n. If I take gamma n into gamma n common, we have the remainder here n plus sign, this is n here, is n divided by m plus n. We have taken the LCM here. If I take m plus n common, then gamma n plus n, this is LCM here. Okay, so if I take m plus n gamma, sorry, it's gamma n plus n and m plus n into common, or LCM, let's say. This will be in the numerator, sum of these two, this plus this. Out of that, we are taking common here. Gamma n, we are taking common. Here m is the remainder. Okay, and this is the n here, remainder. This n plus n and this n plus n cancel out. What we left with? We are left with n gamma n divided by gamma n plus n. This is nothing but this is beta n. This is your left hand side. This is left hand side. So left hand side beta mn has been put. Beta mn. We have finally obtained. We have taken right hand side. We express that in terms of gamma. Then finally we have obtained gamma n plus n. That is beta n. This is the definition of beta n. Now let me take next question. Now 15th question. Let me talk about it. What is question number 15, sir? Let me check it. Question number 15. Okay, so question number 15. Question number 15 says, if n is a positive integer, then prove that you can prove here gamma 1 upon n, gamma 2 upon n, gamma 3 upon n, etc. into the multiplication is in series up to gamma n plus 1 or n minus 1, n minus 1 upon n. This is under gamma n minus 1 upon n. This is 1 upon n, 2 upon n, 3 upon n, and gamma n minus 1 upon n. This is equal to, we have to prove, is equal to how much? 2 pi. Okay, this is twice pi whole power 2n minus 1. Oh, this is n minus 1. So this is n minus 1. N minus 1 upon 2. Power is n minus 1 upon 2. Okay. Upon gamma n. Okay. This we have to prove here. Gamma 1 upon n, gamma 2 upon n, gamma 3 upon n, gamma n minus 1 upon n is equal to twice pi whole power n minus 1 upon 2 upon gamma n. This we have to prove here. Okay, so let me take left hand side. Taking the left hand side here, we are proving here. So left hand side is gamma 1 upon n, gamma 2 upon n, gamma 3 upon n, up to gamma n minus 1 upon n. This we have taken. Left hand side is equal to this. Let's assume that this is the product of these numbers, that p is equal to this whole. This is 1 upon n, 2 upon n, gamma 3 upon n, up to gamma n minus 1 upon n. Let me write it like this. This is the product of these numbers. Now if I express these numbers, now if I write them in reverse order, okay, let me take the first equation. Let me write this as first equation. Now if I write that in reverse order, for that reverse order, Taking that, or P is equal to this gamma n minus 1 upon n means 1 minus 1 upon n. Why? That is there. N minus 1 upon n. And before that, there will be n minus 2. That means gamma 1 minus 2 upon n. Before that, it will be here 1 minus 3 upon n, etc. Up to in the end, this gamma 3 upon n, gamma 2 upon n, into gamma 1 upon n up to n. We have written down then in reverse order. First this and n point here, then n divided by n. N upon n is 1 minus 1 upon n. This is there. Before that, it will be n minus 2 upon n. That means 1 minus 2 upon n, 1 minus 3 upon n, etc. And this 3 upon n is here, 2 upon n, gamma 1 upon n in the reverse order. Let me write the second equation. Multiplying first and second. On multiplication of first and second, we get multiplying first and second, we get left hand side p into p is p square. Now this half, this gamma 1 upon n into gamma, if we that first, gamma 1 upon n into gamma 1 minus 1 upon n. Similarly, gamma 2 upon n into gamma 1 minus 2 upon n into gamma 3 upon n into gamma 1 minus 3 upon n, etc. In the end, we will have n minus 1 upon n gamma under gamma 1 minus n minus 1 upon n. The ending point. I mean, this is the last term. N minus 1 upon n into gamma 1 minus n minus 1 upon n. Okay, now what do you mean by this? These two terms will be going to begin what? Now this we know what, let me write here. Okay, so this p square we are finding the top. So p square is equal to, let me write here. Only we get p square equal to how much? So p square is equal to this gamma n and gamma 1 upon n. Since we know gamma n into gamma 1 minus n is equal to pi upon sine n pi, right? This we know. This formula we have already proved in the previous lecture series. In the 60th lecture series, I proved that y gamma n into gamma 1 minus n equal to pi upon sine n pi. This we have proved already. Okay, or if they are the improper integrals in this, when limits are infinite limits, then this can be in practice. So this is the value. What about this? So these two will give us pi upon this whole value. This first one is pi upon that they are the multiplication. First is pi upon sine pi upon n, because 1 upon n into pi, that is pi upon n. Second is pi upon sine pi upon n. These two, and combination of these two, n minus 1 upon n. Okay, so third will be into pi upon sine 3 pi by n, and so on. The last step, last term will be pi upon sine n minus 1 upon n into pi. Try to understand this value here. So this is n minus 1 upon n into pi. Okay, so this will be pi minus n minus 1 upon n. Okay, now let me multiply them. What do we get here? Finally, p square is obtained as, therefore p square is equal to pi into pi into pi up to n minus 1 times. If pi is for n minus 1, in the numerator we have obtained after multiplication of pi by pi. The denominator we have obtained sine pi upon n, sine 2 pi by n sine 3 pi by n upon n into up to sine, this is 1 minus 1 upon n into pi or n minus 1 upon n into pi. Okay, so this is the last one. Finally, this is, let me take the equation number 1. Very important equation number 1. E square equal to this value. Now, we have to find out this equation of this, this value equal to how much? We have to calculate. So, then p square equal to pi to the power n minus 1 from this, and this whole value will be obtained. So, let me take now other concept. Now, let me take this equation here. This is one of the results which we will require. The p square we have obtained pi to the power n minus 1 divided by sine pi upon n sine 2 pi upon n sine 3 pi upon n up to sine n minus 1 upon n pi. Okay, this equation 1 is very important. We will utilize this to find out our results this one. Okay, because we have to find out these values, value of p here, because we have considered this as p, this whole value as p. So p we have to finally find out. First, let me find out how is this. This is the first equation we have required. Now, from trigonometry, we know that. Okay, from trigonometry or trigonometric functions, trigonometric functions or equations, we can find out what is x equal twice n minus 1 equal to 0. We can find out this is equal. This implies that x equal twice n equal to 1, or x equal to 1 whole power 1 upon twice n. This can be written as, this is, let me take cos 2 r pi, 2 pi r, right here 2 pi r, 2 pi r, or 2 r pi to the power plus iota into sine 2 r, 2 pi r, 2 pi r. Okay, whole power 1 upon, this is value of 1. Okay, and whole power 1 upon twice n, where or here r is equal to 0, 1, 2, up to twice n minus 1.